People is Nero Budur from Leuven, and the title is generic Theta Divisor.
Thank you. So I'll talk about not matrix factorization or something like this, but singularity theory in general and hypersurface singularities. So the dream is when you have a hypersurface to understand as much as you can about the singularities of the hypersurface. And I'll talk about one of the oldest hypersurfaces in algebraic geometry, the Theta Divisor, in the particular case of generic smooth projective curves of a fixed genus. And we'll understand the local structure of the singularities completely in this case. That's the goal of this talk. So the advantage of talking about Theta Divisor is that you can phrase things in very old language, which is very basic. So let me start with theta functions. So what is a theta function? So it's a function defined, I work over the complex numbers throughout the stock, and the theta functions are defined on the following space, vectors of dimension G, and symmetric matrices, square matrices, size G, with positive definite imaginary part. So in this space we have a function defined by sending a vector u and a matrix z to the summation over lattice vectors m of e to the 2 pi I m transpose times u plus 1/2 m transpose z times u. And it's not difficult to check that this is a holomorphic function. And it's classically known that this has some quasi-periodicity properties. So if you fix E1, E2J notation for the columns of this
U then.
So,
The very last one is U then.
very last
exponent. ZU. And if
Transpose.
ZU is correct, it's the Robin itself.
Here.
Yes.
The
Next. Should be
It should be a yes.
yeah.
Okay. So let's fix the notation for the columns of a bigger matrix where you put the identity first and then Z. So this is G by 2G. Then the quasi-periodicity states the following: theta u plus e j z is the same as theta u z. And so this is for j between 1 and g. And for the same j, theta of u plus e j g z is e some non-zero factor here. In front of uz, theta uz. And this quasi-periodicity means the following, or implies the following: if z is fixed, then there is a well-defined zero locus in the quotient by the lattice. Theta, zero divisor of the function theta, is well-defined. In CG modulo de lattice. I want to achieve this situation in the case of compact Riemann surfaces. So if you take C to be a compact Riemann surface, of genus G, then form omega, the period matrix for well-chosen bases. So here you have to choose the basis carefully. So you can always choose basis gamma 1, gamma 2g, a basis of H1 with intersection matrix. Exactly this one here. And omega 1, omega g, a basis of holomorphic holomorphic differentials. So if you do this, then omega is of the type Ig, Z, Z as above. So that means we have a well-defined zero divisor, a theta divisor. Theta of C in the Jacobian of C dual modulo de lattice. So that is the divisor that I will be talking about. And with this terminology, the main theorem is the following. If C is a generic compact Riemann surface, of genus G, so I fix the genus, then its associated theta function is up to a holomorphic change of coordinates equal at every point. So I should do this change of coordinates at every point. So the change of coordinates depends on the point. 2 to its first non-zero Taylor term. So the change of coordinates after a fixed point. There is not a global thing. So this has an algebraic reformulation. So I'll formulate something equivalent. So you see is generic. Then at every point on the Jacobian, the theta divisor is embedded analytically equivalent as a germ with its tangent cone. So let me illustrate that. So what do I mean by that? So you have a point on the Jacobian, and it's also a point on the Theta Divisor, otherwise you cannot think about trivial things. And there exists a isomorphism of germs of the ambient space with the tangent space, of course. The tangent space is well known. You look at the origin of the tangent space, such that it induces an analytic equivalence of germs between the tangent cone to the Theta Divisor at X inside the tangent space. The good thing about this is that we know everything about the tangent cone. So this theorem says that we know everything. Well, we know everything about the tangent cone. I'm exaggerating a bit, but this completely determines the local singularity structure of the generic Theta Divisor. So,
Nero, when you say generic, it means outside of what?
Zariski closed subset.
Zariski closed subset. And you know the codimension of the complement or
Codimension could be big. Yeah. So this is yeah. So this is my theorem. Oh. Yeah, which is so I was very surprised I could prove something like this because I thought actually everything is known about curves, especially Theta Divisor. You cannot find this in the literature. Some experts were surprised, some experts were not surprised, but you cannot find this in the literature. Now, my motivation for this started with a paper for a couple of years ago, maybe 3 years ago, of Christian Schnell and Rubio Yang. They worked on the hyperelliptic Theta Divisor. And in that paper, they constructed a log resolution of the hyperelliptic Theta Divisor. And one of the problems they posed in that paper is, how about the generic Theta Divisor? Can we construct a log resolution of it? And then I realized that we don't know everything. And I already had the tools to do this immediately at the time. So I'll tell you how I did this with modern technology, L-infinity stuff and so on. But I didn't dare before that to use those tools in the setup because I really thought you cannot come up with it. So yeah, if you look up in the book by Valero Conorba, Griffiths and Harris, you're not going to see this thing. So.
and just to compare, so how does the Theta Divisor for a hyperelliptic curve looks like with respect to this theorem? So it's very complicated similarity.
So my goal is eventually to prove the same for that hyperelliptic Theta Divisor. It will imply the theorem of Schnell and Yang in that case, but I cannot prove this yet for the hyperelliptic Theta Divisor.
What is this theorem by Schnell and Yang?
The theorem of Schnell and Yang says that if you look at the filtration, the stratification by the Brilnodder loci, the deeper Brilnodder loci of the hyperelliptic Theta Divisor, and if you blow that up in increasing dimension, then that is a log resolution. And they conjectured that the same was a question that how about the same thing for the generic Theta Divisor? And this is one of the corollaries of this. I'll mention I'll mention this. So to get there, let me recall some classical notions about curves. You have the Brillo de loci. This is the classical notation, WRD. So these are isomorphism classes of degree D line bundles on C, such that they have at least R plus 1 global sections. These are the classical Brillo de loci. And in this notation, and peak 0 is the Jacobian. Peak D, for any D, is isomorphic to peak 0 if used translation by any fixed divisor class of degree D. And theta is the image in the Jacobian of W0 G minus 1. So I will be working with W0 G minus 1. So here, if the degree D is G minus 1. So we'll take G minus 1, then you get a theta divisor as a classical Riemann loans. And what I was saying about the tangent cone, this is a famous theorem of Kempf. Namely, the tangent cone for any theta divisor doesn't have to be a generic one, a generic curve. Is so it is the tangent cone at the line boundary corresponding to x in W0 G minus 1, and is given by the determinant of a square matrix of linear forms on the tangent space, and this square matrix of linear forms is given by the so-called Petri map. And the Petri map takes H0 C L, multiplies classes in H0 omega C L inverse into H0 C omega C. So it's the usual multiplication map here. We're going to call this pi L. So the tangent cone scheme theoretically is determined by the Petri map. In the generic case, you have something even better.
So, can you please expand it as well from here? So, how do you get the matrix?
Yes. So set duality will tell you that this is the dual here. Yeah? And now if you fix bases here, you get a linear form here as the image. That's how you get the, from fixed bases here, you get an element here, therefore in the dual here. The dual is the linear forms. So in the case of generic curves, Giesecke proved that the Petri map is injective. If you think about it in terms of the associated matrix of linear forms, this means that the matrix of linear forms is generic. the matrix xij, xij independent variables. So determinant of the xij, that's the generic determinant hypersurfaces. We know a lot of things about the singularities, and that's why in the generic case this completely determines the singularities of the Theta Divisor. So as a consequence, now we know a lot of wealth about the singularities of the generic Theta Divisor because of this statement. The statement, the theorem that I put on the board can be generalized a bit. So we can replace the complex numbers with any field K of characteristic 0. That's algebraically closed. We have the embedded equivalence of the singularity with the tangent cone in the complex analytic setup. We can replace that in the algebraic case with the étale germs, the étale version of it. That's a bit stronger, I would say, or big. I can replace the Theta Divisor with the real Noether loci, but again for a generic curve. And another generalization is that instead of requiring that the curve is generic, I'm just requiring that the Petri map is injected. And the last generalization is that in fact I can do this for twisted Noether loci, where I can instead of having here just L, I fix a stable vector bundle of higher rank, arbitrary degree, and I consider a twist with that vector bundle. And the same holds. So let me state that. I will need some more notation for that. So C now is going to be genus G. Smooth projective algebraic curve over F algebraically closed field of characteristic 0. F is a fixed. In fact, the bundle that I fixed doesn't have to be stable. Just a vector bundle. On C. We go to moduli of stable vector bundles instead of just line bundles. Of rank n and degree d. And inside here we consider the analog of the Noether loci, but I have a different notation for it. WKF, so these are twisted higher rank Noether loci. These are stable vector bundles such that H0 of E tensor F is greater or equal than K. Yeah, so you can, this is a generalization of this WRD. You have to pay a little bit of attention to the classical notation. So we have an analog of the Petri map here, which depends on E and F. H0 of E tensor F multiply with H0 of E dual, F dual omega C, and that goes into H0 of E, tensor E dual, tensor omega C. So it's the usual multiplication map, and then the data goes into, also there's a factor F tensor F dual, and you take the trace of that to just land in here. So it's a natural map. I will denote the dimension here by L, the dimension here by L prime. And again, you can either view this as a linear map or you can view it as a matrix of linear forms on the dual of this vector space. And if you do that, then the injectivity of the Petri map is equivalent to the associated matrix of linear forms to be generic. So the statement is the following. This is the general statement. We assume that this Petri map is injective. Then we have a embedded étale equivalence of germs with a tangent cone. So there is a étale isomorphism of germs of the ambient moduli space. Tangent space. Which induces an equivalence of the tau germs between this twisted higher rank another loci at E and the tangent cone. That's the first part. The second part is older. So as I said, it's due to Kempf for the Theta Divisor, and it was in the book by Albarino, Cornell, by Griffiths and Harris. It was generalized for all the other loci. So discovers these cases. And then this statement that I'm going to say here is actually due to Polishchuk. In 2004. And I recover it with my methods quite naturally and fast. So it says that the tangent cone is completely determined by the Petri map. So it's given, is defined by the ideal of L minus K plus 1 minus L of the matrix of linear forms associated to this. So let me denote that matrix by star. Yeah, recall this matrix here is generic. So again, we get the determinant of variety, and there are lots of things known about the singularities of determinant of variety. So automatically, we get lots of things about the singularities of
So Nero, so to speak about somehow unit variables, to speak about minors and the corresponding affine variety. So it's
yeah,
so you have
you can feel free to fix bases here, and then you get matrices, Anders matrices. But it doesn't matter if you choose other bases, you get the same varieties. Let me just mention here, there is a result claimed by Teixidor that says that if C is generic and F is generic, then the tetromap, in the case we're working again with line bundles, is injected. So some twisted generalization of the Piscator's result claimed by Teixidor. So you can replace in that case this assumption with this. Okay, let me mention some corollaries of this theorem, but I will not mention them for this twisted thing. Of course, with this theorem, we recover most of the known results about the structure of theta divisor or Brilliant loci, and you extend those to twisted cases. I will only state what is new, what is something that I did not find in the literature before, and only for classical Brilliant loci. So for C generic, for classical Brilliant loci, the new results, among the new results are the following. So I'm going to assume here, for sake of simplicity, that L prime is greater or equal than L. So this dimension is greater or equal than that dimension. You can always get to this by using subduality. You can get back to this setup. So you're not losing actually anything. So the local Bernoulli polynomial of W0D at L is completely determined. That's because someone has figured this out for the generic determinant of varieties of the particular shape. Blowing up pick D at the following chain of subvarieties of WRD in this order produces a low resolution of WRD. This stratification of WRD here is Whitney. And you have explicit computations, local level obstructions. I will now write it. There is something called the topological zeta function of a hypersurface singularity. For WRG minus 1, this is explicit. This is related to the monodromy conjecture of Gusa, Deneffer-Lezer, that says that the poles of the topological zeta function should be the roots of the B function. And now we can check that. So we get, in particular, that the monodromy conjecture holds for the generic Theta divisor. We're still missing the Bernoulli polynomial for r different than 0. In other words, for that particular generic determinant of variety, there's still some things to be computed. We know some things about generally determinate divisors, not everything, but we can still use what's known. There are other measures of singularities like minimal log discrepancies. And those of WRG minus 1 we know now explicitly. Computations of multiplier ideals, Hodge ideals, one of the latest fashion in singularity theory. Again, we can do this here. Low canonical threshold, that was actually for WRD, that was computed by Zhu by different method, but it follows immediately from what you know about low canonical thresholds of generic determinantal varieties. And this formula was remarked as a curiosity in Zhu's paper. Why is this agreeing with generic determinantal case? And now this is the explanation why. These three things here, these are answering questions posed by Schnell and Yang. Positively, Schnell and Yang only posed them for the generic Theta Divisor, but this answers them for generality. And also in this higher rank twisting case, which I didn't write down. So, how does one prove this theorem? So there are two steps to the proof. The first one is to prove it at the formal germs level. And then the second important part is to pass from the formal embedded equivalence to the complex analytic or étale equivalence. And for that we use a embedded version of Artin approximation. I don't claim that there exists an embedded version in full generality. This embedded version that I could do was really when you have a smooth ambient space and you're trying to prove, and you have this formally, with a tangent cone. So I don't, it's not a very general embedded version, but it seems to work. It works very well for the tangent cone. It might be possible to improve that, but I don't need it, and I don't claim to know how to prove very general embedded version. So I will not talk about this, although that's important. Let me just focus on the formal statement. So I want to prove that there exists an isomorphism of the completions here that induces an isomorphism of the completions here where you have a K. And in fact, this is where I had the theory with my co-authors already waiting for this to happen. So this is the formation theory with cohomology constraints. So this is an enhancement of the deformation theory principle of Deligne. That was in terms of differential graded Lie algebra, molar Cartan equations. But the deformation theory of Deligne was also improved, made more flexible by Bukai, Kontsevich, and others by using L-infinity algebras and molar Cartan equations in that setup. So this will be an enhancement of that. So how do we do that? So what do you want to do with deformation theory with cohomology constraints? So you have a moduli space, let's say M, and you have an object there, E, and if you want to understand the local structure of M at E, that's deformation theory, but Now suppose that you actually have a cohomology theory, so then you can define strata here given by cohomology dimensions. So let's say these are vector spaces over C, and you take their dimension, and the ith cohomology, whatever that is, should have dimension greater than or equal to 8. So these are very general terms. Yeah, but what you want to understand is the formal completions of all this as embedded things into each other. So all formal germs of M and this cohomology jump loci at E. That's what you want to understand. Of course, M is itself one of these guys by setting K equals 0 here. Yeah, so it's all together. Here's what our principle says. So first, I did this with Botong Wang for differential graded Lie case. There's always the DGLA governing the deformations of the, that's Deligne's principle. That's C. And all these other germs are controlled by a DGL module over C. And I'll tell you soon how you control that. The enhancement, so there is a more flexible version where we replace the DGLA by its cohomology as an L infinity algebra, and M by its cohomology as an L infinity module. So this enhancement is with my old student Rubio. And of course, this two gives the same deformation functors. So how do we do that? So let me fix some notation here. The L infinity algebra structure means that there's some higher order multiplication maps. Of degree 2 minus d, 2 minus n. However, there's no differential here because that's one of the good things about this theory. M2 is the inherited Lie bracket from the GLA. And the L infinity module is also has some higher order multiplication maps as well. And again, these are of degree 2 minus n. And again, there is no differential here. And M2 is induced by the algebra product from the DGL case. Okay, so how do we control all these germs? At E. So we want the completion at E. So we have again, we have to write down some kind of deformation like functors for every I and K. And you take Artinian algebras, Artinian local algebras over C. And we associate a set. And this set, first of all, you are looking at deformations in here. So you have to involve the Moller-Cartan equation. Omega in H1C. Twisted with the maximal ideal of A. And then the Moller-Cartan equation, but you have to remember that you are in the L infinity setup, so you have to involve all the operations, not just M2. That has to be 0. And so that's just the Moller-Cartan equation. If you stop here, you get the formal germ of M at E. But then you have to go deeper, so you need extra equations. And the next equations are given by the following gadget. By an ideal. Yeah, so there are more equations. So this is given by the cohomology jump ideal, which I'll define soon, depending on I and K, of a a complex of A modules, and I'll write down this complex of A modules. So that has to be 0. I'll make everything here explicit. At the end of the day, you have to model by the analog of the gauge equivalence in this setup. But that's your functor. So let me state what's here. So the complex of A modules is the following. So you have now to evolve the module, reduce it by A, and you put a differential on it as follows. You involve the higher order operations from the module as well. Here this omega. Because of the Maurer-Cartan condition, you will have that this is a complex. This differential squared is 0. Now, what is this cohomology jump ideal? So this is a generalization of the fitting ideal for finitely generated modules over a material ring to a complex. So here we need to have a bounded above complex over material ring with finitely generated cohomologies. So how do we do that? What's the definition? First, you take a free resolution of this. It's going to be bounded above. So this free resolution of your complex is a bunch of differentials, and this is by definition the ideal of minors of size the rank of Fi minus k plus 1 of the I minus 1 map in that complex, and the so you form you make a bigger matrix out of these two differentials, and you take this specific rank minors. That's the ideal of minors of this size of that matrix. And it's independent of F here. So it's really the fitting ideal version for complexes. If you just have one module, you get the classical fitting ideals here. So this is well defined.
Where is the complex coming from?
Sorry?
Is it part of the data in the brace? The complex, where is it coming from?
Yes. So this complex here depends on omega. Omega is a Maurer-Cartan element.
Yeah.
And because it is a Maurer-Cartan element, this operation here is a differential. So this, you input things from here. So it becomes a differential on this.
That's your complex.
This is the complex.
I see.
So of course, then you have to resolve it if in order to use this definition. But this is deformation theory cohomology constants. So it's very neat. So now you'll see that if you apply this for the case of curves, it just spits out things immediately. How do we do that? So first of all, a general fact, if X is a smooth projective variety over the complex numbers, let's say, or algebraic closed field of characteristic 0, and E is a vector bundle on X, then the controlling L infinity pair here so you can pose the question of deformation with cohomology constraints on E even without asking for moduli to exist. Yeah, that's a classical thing. And the controlling L infinity pair in this case is just the cohomology of So maybe I want to control actually this cohomology, or I fix a twist. So let me fix that twist. First of all, you're deforming E, and this is what controls, as an L-infinity algebra, deformations of E, the cohomology and endomorphisms. And then the cohomology constraint come from the following L-infinity module. So this is with the L-infinity algebra structure, and this is with the L-infinity module structure. In practice, you always obtain something like an L-infinity automorphism algebra and the object itself that you're looking at. So now, if X is a curve, dimension 1, because of dimension reasons, there are not that many cohomologies to look at. Plus the degree reasons, here, these are graded degree 2 minus n. A lot of these maps, a lot of the mu-n's and mu-n's do not matter anymore. And if you just write it down, then you get.
So, Nero,
Yeah.
I see here L-infinity algebra, but you say it is L-infinity.
I say L-infinity. So, yeah, this is an A-infinity algebra as well, but it has an L-infinity structure. Yeah. So let me make a remark. Even if you start with an A-infinity algebra and you want to consider it as an L-infinity module over itself, then if that A-infinity algebra structure is trivial, the L-infinity module structure does not have to be trivial. So I'm really using L-infinity here. Just like I'm using here DGLAs or DGL modules. Yeah, I'm really in the league setup. Okay, for dimension 1 and degree reasons, mu n is 0 for n greater or equal than 2. Of course, this is a classical statement that H1 of this is really the local, is that the moduli space in that case would be smooth, and this is its tangent space. One more thing. If F, maybe I should put it here. Here, if E is stable, then this simplifies things. There is no more gauge equivalence to mod alpha. And that's one of the reasons why we work with stable vector models. No, not necessary. You'll mod out by this action. In fact, this action is trivial. You mod out by it doesn't do anything. So that quotient disappears. This simplifies things. This equation then simplifies. It is just given by the V bracket then. This one should be equal to 0. And now you have the other operations here, but because of degree 1, dimension 1 and degree reasons, the only contributions here that matter are the following. And only the restrictions of Mn plus 1 to this notifications matter. In principle, these things combine various cohomology degrees, but only these things will matter. And of course here for n equals 1, this is the Petri map. So if you plug this in to the formula here, so you have to do this cohomology jump ideal, you get the following. So I'm not going to use this as a functor because now I actually have a space, a moduli space, so I can globalize. I can work with the spectrum at the original and affine space. So so you get the completion at E here. Is isomorphic. So this is the tangent space. So it's a smooth moduli space, and this is the tangent space. We complete that at the origin. That just comes from this effect here. Of course, this is classical, but you get it very fast with our methods too. And the other guys, we only need V0K, we're in the curve case. So then I have to apply this, but I'm going to globalize instead of working with local Artinian rings. So I'm going to take the zero locus of some ideal, and I'm completing them at the origin. And what ideal do I have to look at? So I have to look at the cohomology jump ideal of a certain complex. So I have a complex, I'm globalizing it. So I look at formal power series determined here. So let S be the formal power series on the dual vector space there. I have a complex of S modules here. And it's given by, so now I have to use the module. I have to use this. And what is this matrix here? So now, so it's a complex of S modules. So this is a matrix of formal power series, and I can write its coefficients, its degree, homogeneous degree parts in terms of these multiplications, but I don't need everything. I just need the restrictions to here. So this is a matrix of formal power series. The linear part is the Petri map, or the matrix of linear forms associated to the Petri map. My standing assumption is that the Petri map is injective, which we saw that it means that the associated matrix of linear forms is generic. So if you have a matrix of linear of formal power series, such that the linear parts of those entries are generic, then you can change variables formally. So this is equal with M2 after up to a change, formal change of formal variables. And what's the other thing that I have to explain? Well, this is clearly the tangent cone. the equations for the tangent conda. I didn't tell you what the equations are. I have to interpret this ideal here. So this ideal is the ideal of minors of this size. I already fixed the size. This is L here. So this is ideal of L minus K plus 1 minors of the matrix of linear forms given by the integral. That's the end of the proof. So I think this fits like a glove, this theory for this particular problem. I don't have anything else to add.